Hello everyone, let's study about prism and refraction through prism in this topic. To define prism, a prism is a transparent solid which is bounded by two triangular faces and three rectangular faces. As shown here, the prism contains two triangular faces. So we can call this as face 1 and this face here which is opposite to the face 1. So these two are two triangular faces, and then it contains three rectangular faces. So this is phase 1, this is phase 2, and the phase behind this will be phase 3. So a prism, basically this is the most common type of prism. It contains two triangular faces and three rectangular faces. In this case, as seen here, these two are the triangular faces, this phase 1 and this phase 2, and then this is a face, this is a face, and this whole thing is a face called as the base. Now in this case, if light falls on the prism, if light falls anywhere on this prism, light would refract because light is moving from a rarer medium, which is air in this case, to a denser medium. So light refracts on these two sides. The angle between these two faces, the angle made here is called as angle of prism or refracting angle of the prism. As seen here, this angle made here because light falls on this face and light would refract and come out of this face. This angle made here, which is the same as angle made here, this angle here is called as refracting angle of prism or just angle of prism. Now in this case, if we cut a prism along a face normal to the refracting faces, then what we get would be a triangle, and that is called as cross section. For example, imagine that we have a plane which cuts this normal to the face, cut like this. Then what we get would be a triangular cross section. To make sense out of it, think of this case, something of this case where is what we get. Now these two faces, that is, light falls on this face and comes out of this face. Suppose if we take a plane and pass the plane normal to this, then what we cut would be a triangle, and that is called as its cross section. In this case of prism, what we get is a triangular cross section as shown here. We'll read our triangle cross section. As seen here, we have a triangular cross section. Let's call this point as, say, point P, and this point as point Q, and this has some point R. So we've taken 3 points called as point P, Q, and an R. The angle made here is called as angle of prism or refracting angle of prism. Let us call it as angle A. Now let's assume that light falls on this face of the prism. So light falls at an angle to the normal to this face. Let's call this as N dash, and we'll call this as, say, some BC. So BC is the incident ray on the face PQ. Let this be the rarer medium, for example like air, and the prism will be a denser medium. So this light ray, instead of going like this, if nothing was present, the light ray would travel in this direction. We'll call this as, say, some point B and some point D somewhere here. So this B, the CD, this is point C, this is point D. This CD is called as direction of incident ray. That is, light would have moved along CD if the prism was not present. The angle made by BC with N dash, we'll call it as angle of incidence I1. And this angle here, the light refracts, and then instead of going along CD, the light ray would bend towards normal. So assume that the light ray bends like this. The angle made here is called as, say, R1. Let this be some point E. Again, here also, if you draw normal to this point, something of this kind, we will call this as M dash. Now this light ray is now moving from denser to rarer medium. So this light ray would bend away from normal, and finally the light ray would emerge out, say, like this. The angle made here, we'll call this as R2, this as some I2. So let this be EF. So for the phase PQ, BC is incident ray, CE is a refracted ray. For the phase PR, CE is incident ray and EF is the refracted ray. For the entire prism, BC is the incident ray, CE the refracted ray, and EF is the emergent ray. Now the light ray, instead of coming along CD, comes out as EF. So if we draw this EF backwards, then the angle what it makes here, we'll call this point as some point G. This angle made here is called as delta. Delta is called as angle of deviation. Is called as angle of deviation. As seen in the earlier topics, angle of deviation is the angle made between the direction of incident ray and the direction of emergent ray. In this case, this would be delta. So I learned earlier in refraction that the angle made here, we'll call this as delta 1, and this angle is delta 2. So we have ray like this, and this is what is the direction of incident ray, and this is point G, this is point E, this is point C. This angle here is called as delta, and we call this as delta 1 and delta 2. We have studied in refraction that delta 1 is nothing but it will be the angle of deviation for the phase PQ or for the ray BC on the phase PQ. This is equal to I1 minus R1, and delta 2 is equal to I2 minus R2. Therefore, from this triangle, delta here is the exterior angle, and we know that the exterior angle is equal to sum of opposite interior angles. So in this case, delta is equal to delta 1 plus delta 2. Putting the values of delta 1 and delta 2 from here, what we get is delta is equal to I1 minus R1 plus I2 minus R2. If we bring the terms I1 and R1 together, then what we get is I1 plus I2 minus R1 plus R2. So this is the total deviation produced. What is seen from here is this deviation produced depends on I1 basically, because I1 controls R1, R2 and I2. So it depends on I1 basically. Now what is seen is, what you understand is, by taking different light rays, that is, by taking one light ray to fall at an angle like this, where it is I1 is 0, and by slowly changing I1 at different angles. Example, here I1 is increasing and light falls like this. In this case, I1 is 0 basically. In fact, here earlier it was 90 degrees, because whenever the light rays moves on the surface, so here this I1 will be 90 degrees. So by making I1, for example, if a light ray falls along N dash, for this light ray I1 is 0. So for this light ray I1 is 90 degrees. So the value of angle of incidence varies between 0 to 90 degrees. So what is seen is, when I is changing continuously, delta also will change. So let's draw a graph for us. A graph for this. When you plot a graph of angle of incidence with deviation, so this is angle of incidence I, and this is delta, which is deviation. What is found out is, that the variation goes like this. That is, at one point the deviation is minimum, and that is called as capital D. Capital D is called as angle of minimum deviation. Angle of minimum deviation. Some books write this as delta minimum. Again, here it's more like a fact to be understood. We can prove it by using geometry also. That is, if required, we can draw the light rays and then find out what is delta in each case. But it's a time consuming process. Rather, there is an experiment based on this in class 12 experiment. You could try and see there also. Otherwise, just learn the fact that when I is increasing, for example, as we go along like this, I is increasing. So if you draw different lines here, in each case, as I is increasing, delta is decreasing. So what we find is, as I is increasing, delta is decreasing. For some point delta is minimum. Now in that case, we draw a line somewhere here. For example, if you take a point here, we draw a parallel to the x-axis, then at this point we have two angles of incidence. In this case, if you call this as I1 and this would be I2. So what is seen is, for two angle of incidence, delta is same. That is because, as seen from the graph, as I is increasing, delta is decreasing. For example, think of this delta as some 50 degrees. So at some I1, delta is 50 degrees. As I is increasing, at some point, think of this as 30 degrees. So the deviation is decreasing from 50 to 30, and it is increasing from 30 to, it goes on. Example, think this as some other value. So it is decreasing, becomes minimum, and then increases. So for these two angles basically, I1 and I2, delta is same. Now what happens when the deviation minimum? So in this case, we find that I1 is equal to I2. So this is what happens in condition of minimum deviation. In this case, when this happens, when I1 is equal to I2, that is, in this case, the angle of deviation is minimum. In this case, even R1 is equal to R2. Also, what happens is, in this case, when delta is minimum, the refracted ray, that is, this light ray which is refracted, this light ray moves or becomes parallel to the base of the prism. This happens only when the angle of deviation is minimum. So remember these points also. Make sense out of it to understand as to why this is happening, as to why we're getting two angle of deviation. You can think of a case where, suppose imagine a case where, suppose here we put a plane mirror such that this light ray falls normally to the plane mirror. Now what will happen is, in this case we have already learned that if the light ray falls normally onto a plane mirror, the light would retrace its path. So in this case, this is point F. This FE becomes incident ray. In that case, I2 becomes angle of incidence, and light refracts along EC, and light comes out along BC. So in that case, I2 becomes angle of incidence, and this I1 becomes angle of emergence. Even for this case also, delta remains same. So whether light ray moves along path BC, CE and then EF, or light ray moves along the path FE, FC and then CB, in both the cases the deviation is same. That's the reason that for two angles we get same deviation. Now based on this, we have a very important derivation, which is to find expression for refractive index of a prism in terms of minimum deviation angle. So let's consider the cross section of a prism. Let this point to be P, 2 and R. Let the refractive index of the surrounding medium be N suffix S. This stands for refractive index of surrounding medium, and let the refractive index of prism be N suffix P. The suffix P stands for prism. And also let's assume that the refractive index on this side also is same. Now we'll take a light ray which falls on the face PQ. Let's draw normal at this point, and let this be called as N dash. The angle of prism is A. Let this be BC. So here BC is the incident ray. Light would have traveled along this direction if not for the prism. The angle made here is angle of incidence, which is called as I1, and light refracts, and light say moves like this. I'm drawing a light ray which is refracted and moves parallel to the base of prism. The angle made here is called as R1, and then here if you draw normal, if you call as M dash, this as point E, the angle made here is called as R2, and the light ray emerges out finally. Let's call this ray as some E, some point F here. This angle was I2. When we draw light ray backwards, that is when you draw EF backwards, it appears as though EF is coming from some point here. So let's call the point where light rays meet as D. Here CD is the direction of incident ray. As seen earlier, this angle is called as delta. So here we need to find the expression for angle of minimum deviation as well as the prism's refractive index. Let's call as this something else, because the term D is reserved for angle of minimum deviation. Let's call this as point, say, G. So using Snell's law, the surface PQ, then what we get is n suffix s sine I1 is n suffix p sine R1. This we call as 1. Now what we'll do here is, we also know that delta was given as delta 1 plus delta 2. Recall that this angle here was delta 1 and this was delta 2. Basically here delta 1 is the angle of deviation for the ray BC when it falls on the interface BQ. That is, for this surface BQ, the light ray, instead of going along BG, goes along C. So this is deviation here, and also this is deviation for the emergent ray. So delta 1 was given as I1 minus R1 and delta 2 is I2 minus R2. Putting it back in delta, delta is equal to I1 plus I2 minus R1 plus R2. Let's call this as 2. Now here we need to find the relationship between refractive indices and angle of minimum deviation. So let's consider quadrilateral we call this as TC. Before that, let's draw these normals backward. If we extend normals, then what will happen is these normals would meet at a point. Let us call that point as point H, because in this case BC HE would give us a quadrilateral. So consider quadrilateral PCHE. So I'll read out this. It's like this. So this is point P, C, point H. Point H is the point where the two normals meet when they're extended. This is point E. So in a quadrilateral there are 4 angles. The angle at P plus the angle at C plus the angle at H plus the angle at E. This is equal to 360 degrees. But angle at P was called as angle of prism A plus angle at C. Remember, the CH is normal to the surface PQ. Therefore, the angle made here would be 90 degrees, because CH is normal to the face PQ. Similarly, PE is the normal to the, similarly EH, this EH is the normal to the face PR. So even here the angle made would be 90 degrees. Therefore, the angle at this point C would be 90 degrees plus at H it is unknown, plus angle at E would be 90 degrees. The whole thing is equal to 360 degrees. And from here this would be 180. You take this side, it becomes minus 180 degrees. Therefore, we get A plus H is equal to 180 degrees. Now let's consider triangle. Consider triangle CHE. It's like this. So this is C, this is H, this is E. The angle made here is R1, this is R2. We know in case of triangle that the sum of three angles is equal to 180 degrees. So R1 plus R2 plus angle at H is equal to 180 degrees. Let's compare this equation. If you want, we can call this as, say, 3, this as 4. Let's compare 3 and 4. So from 3 and 4, to compare, the right hand term is 180 degrees, and here there is H, and there is A here, and there is R1 plus R2. That means that you can say from these two equations that A is equal to R1 plus R2. It's called as 4, or rather 5. Now what we'll do is, we'll assume that the angle of deviation is minimum. We saw that when we plot a graph of angle of incidence versus angle of deviation, what we find is, we find a curve such that curves of this form, at some point the angle of deviation is minimum. We call this as capital D. The corresponding point, at this corresponding angle of incidence, we saw that I1 is equal to I2. For other angles, example somewhere here, for this angle of deviation, just call it delta itself. For this, I1 and I2 are different. So what we saw here is, in this condition, three things are observed. That is, I1 is equal to I2. Second thing is, we get R1 is equal to R2, and also we realize that refracted ray is parallel to the base of the prism. And what happens is, in this case, delta becomes capital D, that is the angle of minimum deviation. In that case, phi becomes, look at phi was given as A is equal to R1 plus R2. So this phi becomes A is equal to, since here R1 and R2 are equal, we'll just call it as R1 plus R1, or A is equal to 2R1, or R1 is equal to A by 2. This is what R1 is in terms of A. Let's recall what is delta from 2. So from 2, delta is equal to I1 plus I2 minus of R1 plus R2. So in this case, I1 and I2 are equal and R1 R2 are equal. Therefore, delta becomes capital D is equal to 2I1 minus, it was R1 plus R2, but we know from phi that R1 plus R2 is equal to A. Therefore, this be A, or from this, delta plus A is equal to 2I1, or I1 is equal to A plus d by 2. So we know what is R1 and what is I1. Let's recall what was question number 1. 1 says ns of sine I is equal to np of sine R1. When you put the values of I1 and R1, and what we get is, I'll rewrite what is 1 here just to make it more obvious. So from 1, I'm just rewriting 1. So ns into sine I1 is np into sine R1. So ns into I1 was a plus d by 2. It is sine of it. It becomes sine of a plus d by 2 is equal to np into sine R1. R1 is a by 2. Therefore, it becomes sine of a by 2, or np is equal to ns into sine of a plus d by 2 by sine of 2. This is the required expression for refractive index of prism in terms of angle of minimum deviation. Now, in most cases, prism is kept in air. Therefore, if ns is equal to 1, then we have only one other medium. So let its refractive index be n. Because for air, the value of refractive index is 1. Therefore, we have only one other medium. We will call its refractive index as n. Therefore, this equation becomes n is equal to sine of a plus d by 2 by sine of a by 2. So this is what most books will write. But remember the general form, because these general forms are more useful for numericals.